Hello, good morning everybody. In the connection of the virtual work method, and we are going to be trying to solve the one more problem on that part. In the last problem we do have seen that the two balls are going to be rested on AC bar as well as the BC bar, and we assumed that there is a virtual displacement is going to be existed. Now in the same connection we are going to be taking another problem where the ladder is going to be rested on the vertical wall as well as on the horizontal surface. So these practical examples everybody has come across in their own life. So now we can see the problem is that a ladder AB of length L and the weight W. As we know, this is going to be the length of the ladder is L and the self weight is going to be acting from the centroid of that object is the W, and stands in a vertical plane supported by a smooth surface at A as well as the B. So in this case what happened? So it is going to be the vertical plane is supported and the rested on the horizontal plane that I am going to be considering here. That's going to be the horizontal surface is going to be your A, and the vertical wall I am going to be where it is going to be have a contact that I am going to be say the B. Using the principle of virtual work, find the magnitude of the horizontal force P to the applied at D and A. So we need to be calculate how much force we applied at the A. So that we need to be calculate here if the ladder is to be in the equilibrium condition. So as we know that while you need to apply this principle of virtual work, first we need to apply the virtual displacement. As we know that in the last problem we do have calculated some of the parameters that's going to be x, and x1 and x2 we do have calculated, and we did the derivation. That the derivation itself is going to be your infinitesimal displacement. Now the same case we are going to be applying here. So in this case, can you see this is going to be your OB is going to be your vertical wall and OA is going to be your horizontal surface. So then it is going to be making with the horizontal plane is going to be the theta. So now I need to be find out OB distance. Suppose if I am going to be taking the sine theta, as well I know the AB is going to be your ladder, that's the length is going to be the L, right? And in this case what will happen, I am going to be taking the sine theta. What is the sine theta in this case? The sine theta is going to be opposite side is going to be the OB and the diagonal is going to be the AB. That's going to be OB by AB I am going to be taking. So same, the OB I am going to be considering that as a Y. The YAB is going to be your L. That L I have taken. Then finally the Y is equal to, what is the formula we are getting? The Y is equal to L sine theta, I got it. Right? So this is going to be the actual length when it is going to be when the ladder is going to be supported to the vertical wall, but we need to be find out the infinitesimal displacement. At the same time I am going to be calculating the x over here. What is the x is equal to be? X I need to calculate cos theta is equal to OA by AB. So the cos theta is equal to the formula OA by AB. OA I am going to be considering with respect to the x value, that's going to be AB is the L. The finally x is equal to L cos theta, I got it, right? So now I have found the y value as well as the x value. Now what I am going to do, I need to give a infinitesimal displacement at the point A or at the B. So then I can calculate the force P. So in this case what will happen, when the force P is going to be acting at A, so then the displacement of the A is going to be coming towards the left side, then this is going to be called your A dash. Right? When the A dash is going to be there, automatically the B is going to be shifted to the another position. This is going to be your B dash. Now I am going to be joining these two. Can you see this dotted line is going to be representing the virtual displacement of the ladder, and then this B dash I am going to be say the dy, and A dash I am going to be say that's going to be your A dash is going to be dx I am going to be say. At the same time the center of the gravity of the ladder also shifted to C dash. So the distance between your C to C dash I am going to be taking here is the dy by 2. Once you are going to be symmetrical triangle, suppose if you are going to be applying, then you will get that's value dy by 2. So what I am going to do, I am going to be deriving this y value in terms of the theta. So that's going to be dy is equal to L sin theta will going to be your cos theta and theta will going to be your d theta. Can you see dy we got it? And similarly, the x is equal to what you are going to be calculating here, that I am going to say a dash is going to be the dx. So that is equal to dx is equal to L minus sine theta and d theta we are going to be getting. But can you see the dx and the applied force are moving in the same direction? That's why I am going to be taking the modules over here. Then finally, the dx is equal to L sine theta d theta, I will get it. Can you see x value and the infinitesimal displacement in the same direction we got it, and the y value infinitesimal displacement in the vertical direction we got it. Now I am going to be taking into the principle of virtual work. Now we need to apply the principle of virtual work. So in this case, what will happen? The total work done acting on that member, the total virtual work acting on that member is equal to 0. Before that, we need to find out how many forces are acting on this member. There we can see at A, the force P is going to be acting. At the C, the self weight of the ladder is going to be acting. So now, as we know that the displacement of the A dash is going to be your dx, we got it. So that P into dx. Similarly, the self weight is going to be the W, that is going to be dy by 2 we are going to be getting. So the total work done, the total virtual is going to P into dx, we got it, plus W is going to be the self weight of the member, that's going to be, the distance is going to be dy by 2 is equal to 0. But can you see the displacement of the P at the A point is going to be in the same direction of the applied force. But in this case, the W is going to be, can you see, it is shifted. But the self weight is acting in the downward direction, but the displacement is occur in the upward direction. So that I am going to be taking again here with respect to the minus. So I am going to be substituting these values in this equation. Then we can find out the value of the P. So then the P into dx is equal to, what is the formula? L sine theta d theta. This parameter I am taking towards the right side, that's going to be W. The dy is equal to this formula, what I am getting, that's going to be L cos theta d theta W by 2. So then I am going to be L will going to be cancelled, d theta will going to be cancelled. So then what I am going to be taking, the P value we need to be calculate from this one, how much force we need to apply at P so that the body is going to be at the equilibrium condition. So the P is equal to, what is the formula? W by 2 cos theta by sin theta. So from this one, the P is equal to W by 2 cot theta, we will get it. So when we know the magnitude of the P, if you want to calculate, if you know the self weight of the system at what incline to the horizontal plane, then automatically we can calculate the applied force at A easily. So I hope you people are able to understand the main concepts of the principle of virtual work. As we know, the principle of virtual work, we are not going to be calculating how much force is going to be, how much work it is going to be done by the system. But by using this one, we are going to be calculating the unknown parameters like theta as well as the force P, how much it is going to be acting. So thank you.